Hello, my name is Alexis Iaryczower, and here is my Project 1 Most Important Topics for Dr.Hassan Rashidi's class for Spring 2025. The 5 topics I think are the most important are designing for cost, manufacturability, assembly, reliability, and test and maintenance. So the first topic is going to be design for cost, and the 2 important things to keep in mind here are direct costs versus indirect costs. And your direct costs are going to be tooling, labor, purchase parts, and the material that you use. And the indirect are going to be the discount, profit, selling expenses, and overhead. And the direct costs are the costs that you have to keep in mind when you're designing a product. This graph here shows the cost makeup. So 5 is going to be the design, 15% is going to be the labor, 30% is going to be overhead, and 50% is going to be the material. So it's very important to consider what is the cheapest material that you could use when designing a product. This is going to require cost optimization. One of the strategies to do this is going to be a cost estimation. Early stage cost estimation is best so you can keep track during the design process. General cost models can also aid in this, and market research can help gauge what prices competitors have. Another strategy is going to be design for value. This is going to mean that when making design decisions, you have to take into account the value that this adds to the life cycle of the product, the value it adds to the function of the product, and the value it adds for the customer. Another strategy is going to be manufacturing, and we'll get into this more when we talk about design for manufacturing. But the things you have to think about are the type of machining. Some machinings are more expensive than others. The volume you're machining things in bulk can often be cheaper. And simplifying the number of features can also help to make the manufacturing cheaper. The final strategy is going to be having a cost objective, having a goal for what you want the cost to be, and working towards that goal. Now, the reason that this is important is because designing for cost will help you be competitive in the market, help you sell. It'll increase your profits, and it can help you have faster production if it doesn't take as long to gather the funds for the project. A capability of this is that you can balance performance, having the best performance with the lowest costs, but this in turn has the possibility of reducing quality and also can apply constraints to your design if there is a feature you want to have that is too expensive. The second topic is going to be designing for manufacturability. So during the design process, things you're going to want to keep in mind are incorporating this early in the design steps. You don't want to get to the end of the design and have to go back and change your whole design in order to make it easier to be manufactured. You also want to have collaboration between the different disciplines, again, so you don't get to the end and realize a different department needs something that will throw off the manufacturability of your product. You also need to remain organized with your bills of materials. This will help when you reach the end to know what parts are required to manufacture your product. And in line with this, it's just going to have a streamlined data exchange and a good record of all engineering changes, so it's easy to stay organized and optimize for design of manufacturing. So specifically what this is going to mean is to keep in mind your manufacturing process and designing for that. So you can see here for injection molding, you're going to have to include things like draft angles. You're going to have to pay attention to your corner radii. You're going to have constant wall thickness and thin walls. These all deal with the cooling of the plastic and having it easy to remove from the molds, and overall just making sure that there's no defects in the parts. This is going to be important because it can reduce manufacturing time and waste. It'll improve the quality, as you saw with the injection molding example, and it can increase the efficiency of producing the product. It's going to be very important for preventing defects. However, it can limit design flexibility, and it's also going to require more time on the design side of things. The next topic is designing for assembly. So you have to think about when the person or machine that is assembling it, they're going to have to retrieve the part, handle the part, and mate the part within the assembly. So you're going to want to simplify the assembly as much as possible. Some ways to do this are reducing the part count, which means you're going to really have to determine if that part is necessary, and also being able to combine parts. If there's parts that are combined with fasteners that can be made into one part, you should do that. You're going to want to modularize your parts, again, reducing the number of fasteners and implementing multi-purpose parts. If you can take two parts that do different tasks and combine them into one, that's going to make it simpler to assemble. You're going to want to simplify structure. So if you can't combine them into one part, you're going to want things that are self-fastening, snap fits, and things like that. And you're also going to want to design self-locating parts. So you don't want it to be ambiguous where the part goes. You want it to be clear, design shapes that are clearly fit together. And lastly, you're going to want to reduce assembly time. So you want to make sure that the parts are easy to handle. You don't want flimsy parts that can slip through someone's fingers, or things that are sharp that can hurt someone. And you also want to give parts an obvious orientation. If you could have a part that's symmetrical, perfect. But if it's not symmetrical, you want to make it obviously asymmetrical so that the person assembling it knows which way it's supposed to go. And you also want to keep in mind how these parts are going to be stored. If they're going to be stored in bulk, you want to make sure that they won't get tangled or stuck together somehow. So the importance of designing for assembly is that it's going to reduce the time, it's going to make the production more efficient. It's going to lower your cost because you're not having to pay for as much time of the laborers and things like that. And it's going to improve reliability because you're trying to reduce the number of mistakes that are made during assembly. And some limitations of this is that it's going to limit your design flexibility. You'll have to maybe change some parts to be easier assembled. Again, it has more time investment on the design side, and it's not suitable for all products. Some products may not need any assembly at all. The fourth topic is designing for reliability. The process for this is going to reduce the possibility of failure. So you're going to start with defining and identifying. You're going to establish the goals and identify the risks, the failures that might happen with the product. Then you analyze and assess. So you're going to do analysis to estimate and predict what the failure modes are before taking any data. Then you quantify and improve. So this is the step where you're going to test prototypes and iterate on those prototypes to reduce failure. And then you're going to validate, which means to confirm that your tests meet your goals for reliability. And finally, you monitor and control, which means you continue your analysis with field data. When mitigating failure for reliability, the first step is to avoid the failure. If that doesn't work, you're going to want to reduce failure as much as possible. The next step is to transfer the failure to less integral parts of the product. And level 4 is to accept possible failures that are not threatening to the function of the product. Reliability is important because it'll increase the product lifespan. It's going to lower the costs after production because it's going to lower maintenance cost. And having reliable products improves brand reputation. The capabilities of this are to anticipate different failure modes. However, this will result in a higher development cost and can lead to some design trade-offs. The last topic is to design for test and maintenance. Different techniques for this include having easily removable parts, so it's easier to service them. Self-diagnostic capabilities, having sensors and things like that in the product to determine the failures on their own. Quick access panels, again, for ease of maintenance. Minimizing the number of parts that need to be serviced and maintained. And having detailed service documentation, making sure there's an organized framework in place for keeping track of maintenance. Philosophies have changed over the past few years. It used to be that all failure should be put into one disposable product, but now it has shifted into making sure that the entire product is long-lasting and having maintenance instead of just replacing parts. Designing for maintenance improves the reliability of products, is more cost-effective because there's less failure and less replacing of the products, and it enhances the lifestyle of the product when there's measures in place to maintain it. A capability is that it can simplify repairs. However, the limitations are it adds design complexity and again requires time investment on the design side. All of these measures are making sure the product is as best as it can be, and that is why I believe it's the most important.